All right, so in this lesson, we're going to look at series circuits. All right, so a series circuit's a circuit that's connected by a single line. So we'll have pictures of that. So we have here a series circuit. We have it shown. The important part of a series circuit is there's only one path for electrical current to flow. That's really important. There are no branches in a series circuit, a purely series circuit. So here there's only one path for the electricity to go through. Okay, that's going to help us with some of our laws. If there's only one path for the electricity to flow through, the current through each section, so the red section, the green section, the purple and black, if you can see those colors, through each section, the current has to be the same. And that's because the current can only push as fast as the largest resistance. So that's going to slow current down. So there's all these resistors. The more resistance we have, that's going to slow the current down, and it's going to be equal flow through all of them. Okay, so that's the important part. Series circuit, there's one path for current, therefore all the currents are the same. Voltage, on the other hand, we're going to have different drops in the push. Okay, so as this battery starts out, that's your voltage total, your ET. This is your voltage drop at light bulb 1. So you come around, the current comes through, gets to light bulb 1, and because of resistance, some of that push is lost. The current continues to flow, but it's not flowing with as much force as before, and it gets to light bulb 2. Light bulb 2 again takes away some of that force. You could think of it reducing the power of the current. And we lose some force, goes to the third light bulb, we've lost even more force, and then we come back, the electrons come back and they get another push from that battery. Okay, take a look at the pump video. The pump video will help explain that really nicely for you. There's another really good video for this section. All right, so our voltage drops add throughout the circuit and resistances add up. Okay, so the resistance seen by the battery is the sum of all the resistances that are seen at the circuit. And that's because, I mean, you may have, as current flows through, it's a circuit and it keeps going around. So if current is slowed, if you want to think about the first pass through, if you want to think the very first electron that goes, maybe it has a little higher speed here and it slows down, it slows down, it slows down. But eventually those electrons are only coming back at as one electron comes back here, another one can leave this side. Okay, you want to think of it as kind of like a continuous chain. So that's why that all the resistances add together in order to figure out, well, how many electrons or what is the current that is allowed to leave the battery. It's really electrons per second, if you want to think of it that way. It's coulombs per second is an ampere, but it's really, we're thinking about electrons per second that are leaving that battery. Okay, so current's going to be the same everywhere's. Voltage always adds up and resistance adds up in a series circuit. Now, REQ is equivalent resistance. Sometimes I will use RT, total resistance, and that's our resistance at the source. The word equivalent resistance is really nice when we get to combination circuits though. So we'll see that when we get there. Let's do a few calculations. They should be nice, easy calculations for you. I'm going to give you a chart that I often use, and the chart is in your worksheet as well. So you might find this useful. So we want to figure out the equivalent resistance and the current from each battery and the voltage drop across each resistor. So I'm going to give you the chart method for keeping track of things. If you are one of these people that writes all over the place, the chart is great if somebody's marking it and it's not being marked by Sam. So that's one of those little things that you can do for me if you're handing something in. If you're a messy writer, take your notes and organize them in a chart and just hand your work in separately. It can help me find it. Now, my lines clearly aren't very straight. I think that's just how I have my tablet aligned here. So we're going to figure out voltage, current, and resistance. We have 5 resistors. So we have R1, R2, R3, R4, R5, and then we're going to have total. The total is the same as our source. Okay? So we can fill in as much information as we know. I'm going to just sketch some lines across here, as messy as this may look. All right, resistor 1 is 20, resistor 2 is 20, resistor 3 is 20, resistor 4 is 20, and resistor 5 is 10. Now, Kirchhoff's laws, those are the laws that I just gave you, tell us that resistance adds in a series circuit. So what we do is we take all of our resistors and we add them together. So we have 4 20s, which is 80 plus 10 gives us 90 ohms. Whoops. All right. So that's just R1 plus R2, adding them all together. There's one other piece of information I can fill out here from our picture, and we know that the voltage from the battery is 9 volts. So we can put that in here. That's our source. And you'll notice we have current, voltage, current, and resistance going across. These are the 3 things needed for Ohm's law. So I've got my resistance calculated. I know my voltage at the source. I can find how much current is leaving the battery. So in order to do that, we are going to find current is equal to voltage divided by resistance. 9 divided by 90 gives us 0.1 amps. Do you remember what's the same in a series circuit? Current. It's the same everywhere because there's one path for the current to flow. It's like being in a line at the store to get in. Maybe that's the best way to describe it, is being in one of the COVID lines at the store. You know, you get the line and you're waiting to go into the store and you can only go in as fast as people come out, right? Doesn't matter how big the lineup is. If there's only one entrance being used by the store, you can only go in as fast as people are coming out. Electricity is basically the same way. That's the people in the stores, like our resistance. And current is how fast people are coming out to everyone going in. And then the voltage, well, I don't know what we align with that in that scenario. All right. That gives you a visual maybe for current flow. Now that we have that, we can figure out what's the voltage drop at each resistor. We know voltage is current times resistance. So we just use Ohm's law. It's I times R. So 0.1 times 20 gives us 2 volts, 2 volts, 2 volts, 2 volts, and 0.1 times 10 gives us 1 volt. If we've calculated correctly, Kirchhoff's law says the voltage adds up. 2 plus 2 plus 2 plus 2 is 8, plus 1 is 9. We had 9 volts to start, so we know we're correct. So we can kind of do that cross-checking. All right, hopefully that made sense to you. If it didn't, we're going to do a couple more. Example 2. I want you to calculate the equivalent resistance, current drawn from the battery, the voltage drop across each resistor, and the total power provided by the battery and the power dissipated by each resistor. So we're going to add one extra line to our chart. So we'll make our chart up. Thankfully this time we have a little less to calculate. Oops, R2. R3, and I'll say source. Okay. And a column for voltage, a column for current, a column for resistance, and a column for power. Label them. Voltage, current, resistance, and power. All right. First thing we're going to do is we're going to fill in what we know. So I know resistor 1 is 100. I know resistor 2 is 300. And I know resistor 3 is 50. That means I have a sum of 450 ohms. The source is still a 9-volt battery. How much current is there in this particular circuit? So to find our current, we're going to say E over R equals I. So 9 divided by 450 equals 0.02 amps. Okay. And these, I'm just leaving these in their base units. The unit is the same the whole way up. Now, current is the same everywhere, so we know it has to be 0.02 here, 0.2 here. And you'll notice now we can calculate voltage everywhere. So voltage, we're just going to multiply the two of them together, and we find we get 2 volts, 3 volts, and oops, 2 volts, 3 volts, 2 volts, 6 volts, and 1 volt. If we add those together, we get 9 volts. So current adds, or sorry, voltage adds. I keep wanting to say current, sorry. Maybe I've just been talking too much the last little bit. Now I want you, so we have equivalent resistance. The current from the battery is 0.02 amps. Voltage drop across each resistor. We've got 2 volts, 6 volts, and 1 volt. We've got that. And then the total power provided by the battery and the total power dissipated by each resistor. Well, power is just going to be E times I. So we just multiply these two columns. 2 times 0.2 gives me 0.04. 6 times 0.2 gives me 0.12. 1 times 0.02 gives me 0.02. And 9 times 0.2 gives me 0.18. Now let's look at what we have here. We have 0.18. If we take power and we add it going down, 0.04 plus 0.12 plus 0.02 gives me 0.18. So we find power. This wasn't in our original formula, but power adds in a circuit. Okay, so for a series circuit, voltage adds, resistance adds, power adds, and current is the same. It's going to be a little different when we get to parallel. You'll see that. Last example. I'm going to show you another way that I use to calculate these. And I use this method when I have a bunch of pieces I don't know, or more so when I have a combination circuit. So if you don't like the chart method, this gives you another strategy, and it's perfectly acceptable as well. For some of you, it might be easier. Now you notice in this example, we have V instead of E for our voltages, and that's okay. So we want to find the missing value. So when I see a problem like this one, the first thing I do is I go, where can I use Ohm's law? Okay, so I look and see, can I use Ohm's law anywhere? If you can't use Ohm's law anywhere, see if you can calculate the total or equivalent resistance. That's the other one. But we're going to start with, can I use Ohm's law? Because I see right here, I have voltage, I have resistance, I know I can calculate current. Current is equal to V over R, which is equal to 6 over 3, which is 2 amps. Current is the same everywhere, so I can plug it in. So I know everywhere is in this circuit, I have 2 amps because current is the same. That's what Kirchhoff's law tells us. Now that I have that, voltage is current times resistance. So that means I must have 4 volts here, 2 times 2. And now maybe you think you're stuck. So use Ohm's law to find current, to label current everywhere. Okay, so we labeled the current everywhere. 3, we might have to use Kirchhoff's laws or Ohm's law. So we're going to use Kirchhoff or Ohm. Okay, so we have to use one of the two. So I look through, I can't use Ohm's law here. Oh, I could use Ohm's law here. I can find the equivalent resistance. Resistance is equal to voltage over current. So 12 divided by 2 gives me 6 ohms. So, okay, I still can't use Ohm's law here in order to find V and R, but Kirchhoff's law tells us that the voltages add up. So Kirchhoff's law says that V total is equal to V1 plus V2 plus V3. So 12 has to be equal to 2 plus 4 plus whatever V3 is. Well, 2 and 4 is 6. V3 must be 6 if it adds up to 12. So we get 6 volts. Oh, sorry. Just let me erase here. I used amperage. It's not going to be 6. That's impossible. I used the wrong number. I need to use my 12 equals 6 plus 4, which is 10, which leaves me with 2 ohms left over for volt 3, or 2 volts left over. So we'll put 2 volts here, and then resistance is going to be equal to 1 ohm, simply because 2 divided by 2 gives us 1. So that's just another way of calculating. I often will use this method of, if I have enough space, writing things next to each of the resistors. It's one of my favorite methods, to be honest. Hopefully that gives you a good refresh on a series circuit. If you need any extra help with that, please let me know. The worksheet for this section is series and parallel together. So you'll want to watch the parallel circuit before you do the quiz and before you do the worksheet on it.